All right, today we're going to keep going with triple integrals. We introduced cylindrical and talked about cylindrical coordinates last day, and we did one example. Let's do one more quick example, and then we're going to move on to spherical coordinates, and then take a quick look at applications of triple integrals, and we'll be done with them. So we are asked in this particular example to find the volume of some space We're asked to find the volume of a particular solid that's enclosed by three different things. It's enclosed by the cylinder x squared plus y squared equal to 4. If you're just given x squared plus y squared equal to 4, and you're not given any other information, you're going to think that's a circle, which it would be in the xy plane, right? But we're told it's a cylinder, and we're obviously dealing in 3 dimensions. So x squared plus y squared equal to 4 is a cylinder. Z can be any value. If you cut through the cylinder at some particular z value, what do you get? You get a circle, x squared plus y squared equal to 4. Okay, so the outside wall of this solid is enclosed by the cylinder, or is a cylinder. The top of this volume is a paraboloid. Okay, it's the paraboloid z is equal to x squared plus y squared. And hopefully, when you see this now, you should start being able to imagine in your mind what this thing looks like. It's this 3-dimensional paraboloid here. And on the bottom, it's enclosed by the xy plane. So it's got a flat base. And we want to find the volume of this thing. So we basically want to find the triple integral. We basically want to find this triple integral, right? The function we're integrating is just 1 dv. So we're going to triple integrate dv, which gives us the total volume, throughout this region. And obviously, it's inside of here is this region D, our 3-dimensional region of integration. So all we have to do is find the limits and do the integral, okay? And so we've got 2 choices so far. Cartesian, our dv can either be dx, dy, dz, or we can use cylindrical coordinates, in which case dv is r, dr, d theta, dz. Okay, since we're explicitly told in the question that our volume is enclosed by a cylinder, you should probably think cylindrical coordinates are going to be easier, and you would be very right. Okay? So we're going to use cylindrical coordinates. Typically, especially when our volume is symmetrical with respect to the z-axis, you're going to integrate into z direction first. Typically, that's easiest, but you don't have to. And I think in the lecture notes, no, it's going to be a later one where we actually change the order of integration. You could change the order of integration, but typically you're looking for some axis of symmetry like this. And if it's symmetrical with z, well, then we're going to integrate with respect to z first. Okay? Which means our integral that we're solving is going to be r dz, and then we're going to integrate with respect to r and then theta. Okay, again, this is dv. The function we're integrating is just 1 because we're looking for the volume. Okay, so we're going to integrate into z direction first, which means that we choose an r and theta and keep them constant. Okay? Well, r and theta are polar coordinates, which live in the xy plane. So you choose some point in the xy plane which would be inside of the region of shadow of this volume. All right? If we put a light up here and shine it down on this volume, we're going to get a shadow on the xy plane, and that xy plane is going to be that circle, and we call that the region R for the region of integration for the double integral that we are left with after we get rid of z. After we integrate out z, we're just left with a double integral r dr d theta, right? And that has a region of integration r, which is in the xy plane, because that's where r and theta live. So you choose a particular value of r, which would be this distance to this point here in the xy plane in the region r, and it has a certain value theta. And now we draw an arrow from that point through our region of integration in increasing value of z, because we're integrating with respect to z. And we ask, where does that arrow enter the region D? It enters here. Where does it leave? It leaves there. At what z values does it enter, and what z value does it leave? That gives me z min and z max. Z min is very obviously what? This point, what's the z value for this point down here in the xy plane? 0. What about over here? Z is 0 everywhere in R, right? So it doesn't matter if I draw this arrow like this, or I draw it over here, or I draw it over here. It always enters on this flat round bottom in the xy plane where z is equal to 0. So z min is going to be 0, always. It's not a function of r or theta. How about z max? Well, that's where it leaves here. That will be a function of where I draw this line, right? If I draw this line right next to the z-axis, will z max be less than or greater than this z max? If I draw the arrow right here instead. Well, remember, the top of this volume is this paraboloid here. So if I draw my arrow here, it's going to leave that volume at a much lower value of z than here, correct? So z max is a function of r and theta. The coordinates of this point here in the region r in the xy plane, I said, are r and theta. And everywhere on this line, r and theta are constant. But if I choose a different r and theta here, which I could do, my z max is going to be much smaller, because this arrow is going to leave this volume D at this value of z rather than that value of z. And therefore, z max is a function of r and theta. It's going to be a function of this paraboloid here, which we're told is, that paraboloid is z is equal to x squared plus y squared. Okay, but we know that x is equal to r cos theta. We know that y is equal to r sine theta. So you substitute those into here, and what do you get? Z is equal to what? It's equal to r squared cos squared theta plus r squared sine squared theta, which is equal to r squared. Okay, so on this paraboloid, on the top of this volume, on this paraboloid, which forms the top of this volume, z, right, if I draw my arrow going through here, it's going to come out of the top of that paraboloid at a z value. What is that z value? It's r squared, right? If r is bigger, I get a bigger value of z. If r is smaller, I get a smaller value of z, where that my arrow comes out of that paraboloid. Okay? So that means z max is r squared. I'm integrating with respect to z. Okay? Any questions about that? That's really the hard one. Sorta, and that wasn't even that hard. Okay, so once we integrate z, the z direction's gone. Okay, all we got left is r and theta are polar coordinates in the xy plane. All we got left after z is gone is this circular region r. And we got to then integrate with respect to r and then theta. So, okay, I can draw a line from the origin in increasing value of r at some particular constant theta value. I don't know, maybe like that. That would be it for a theta value like that. Everywhere on that line, theta is the same. But r is getting bigger, right? Because we're integrating with respect to r next. So we're finding the limits for r. So what's r min? 0. What's r max? And does it depend on theta? No, because it's a circle. The region of integration is circular. So it's going to be what? It's going to be the radius of that circle. And what is the radius of that circle? Well, for that, we need to go back and remember what the cylinder is. What was the cylinder? It was x squared plus y squared equal to 4. That's the cylinder. If we change that to cylindrical coordinates, replace x with r cos theta, replace y with r sine theta, what do I get? R squared equal to 4, or r equal to 2, right? R equal to 2 is the equation for a cylinder. Z could be anything on the wall of this cylinder. Theta could be anything from 0 to 2 pi on the wall of this cylinder, but the radius is always 2. That defines a cylinder. Okay, so that means the cylinder is always 2, which means R is going to go from 0 to 2, right? Because the radius of this shadow region is obviously the same as the radius of this cylinder. Okay, so R min is going to be 0, R max is going to be 2, and it's independent of theta. So 0 to 2, and what do we got left? Theta. Okay, well now we sweep this thing all the way around, so it goes through the whole region once and only once. Theta goes from 0 to 2 pi. Or if you want to be difficult, negative pi to pi. Pi to pi, yeah. Okay, so that gives us our triple integral. Okay, and now the integration itself is pretty simple. I'm not going to spend time on that. Any questions on how to do the limits? Okay, so that's triple integrals in cylindrical coordinates. All right, well, let's move on and introduce one more coordinate system. Well, one more set of coordinates. So we've got Cartesian coordinates, x, y, z. We've got cylindrical coordinates, r, theta, z. And now we're going to introduce spherical coordinates, which are rho, phi, theta. So again, we'll draw our right-handed three-coordinate system. This is the x-axis, y-axis, z-axis. If we have some point in three-dimensional space like that, we know we can define it with Cartesian coordinates. We know we can define it with cylindrical coordinates, right, where r, theta are polar coordinates. So if I drop that down onto the xy plane, that's r, that's theta. And obviously z is the height of that point above the xy plane. Okay, now we're going to introduce spherical coordinates, which are rho, the Greek letter rho, R-H-O, the Greek letter phi, P-H-I, and theta. Okay, rho, phi, and theta, in that order. So rho is going to be the straight line distance from the origin to the point. Okay, so it's different than r. R is the distance from the origin to a point in the xy plane. Rho is the straight line distance from the origin to our three-dimensional point. Phi is going to be the angle from the positive z-axis downwards. And theta is the same theta from polar coordinates. Okay, it's this theta here. So those are spherical coordinates, rho, phi, theta. Why do we call them spherical coordinates? Because they're very handy for spherical type surfaces. So what would be the equation in spherical coordinates for a sphere centered at the origin with a radius of, say, 1? You've got a sphere centered at the origin, it's got a radius of 1. What would be the equation for that sphere in spherical coordinates? So think of a point on the sphere. How would you define where that point is? Or think about it this way. Which one of these, or which two of these, or which three of these are constrained on the surface of that sphere? That means, constrained means they have to be a certain value. Rho, right? What does rho have to be on the surface of that sphere? It's got to be 1, right? If I draw a sphere here, doesn't matter which point I go to on that sphere, rho is equal to the radius of the sphere. And the definition of a sphere is it's got a constant radius, right? So it would be rho equal to 1, which means phi could be anything on that sphere, or theta could be anything on that sphere, which makes sense, right? You don't have to constrain phi and theta. They could be anything, but rho has to be equal to 1. Okay, so that's basically why we call it the spherical coordinate system. It's very handy when your surface or part of your surface, doesn't have to be the whole surface, but part of the surface is spherical in nature, okay? Okay, well, in order to do this, we're also going to have translations between x, y, and z and rho phi theta. And if you do the basic geometry of this, you'll find that x, right, where obviously x is, right, that's x, that's y, and obviously that is z. So if you do the basic geometry here, you'll find that x is equal to rho sine phi cos theta, y is equal to rho sine phi sine theta, and z is equal to rho cos phi. And this is something we give you on the formula sheet for the final exam, so don't sweat it out that you've got to memorize this. Okay, if you need them, they'll be on the formula sheet. Okay, so we already know for a sphere centered at the origin, its spherical equation is very simple. It's rho equal to whatever the radius is of that. What about the spherical coordinate equation for x squared plus y squared plus z minus 1 squared is equal to 1. Well, first of all, what is that animal? Anybody want to guess? What would it be if it was x squared plus y squared plus z squared equals 1? Oh, come on, that's easy. It's a sphere, right? With a radius of centered at origin, right? What is this one? Also a sphere, right? Sorry, go ahead. Question? It's a sphere, but not centered at the origin anymore, right? It's centered at exactly. It's been shifted up 1 on the z-axis. Okay, so the center of this sphere is at the coordinates 0, 0, 1, where this is x, y, z. Cartesian coordinates. But its radius is still 1. Okay? Okay, so how do we get this? Well, you just take, this is just plain old algebra. Wherever you have an x, you substitute this. Wherever you have a y, you substitute this. Wherever you have a z, you substitute that. Okay? It's a good exercise to do this once. The steps are in the lecture notes. We're not going to waste time doing it here. Just keep in mind that you end up with, whenever you've got x squared, y squared, or z squared in your equation, you're going to end up with a lot of cos squares and a lot of sine squares, right? So when you have that, look for common factors of those terms that when you take it out, you're left with cos squared plus sine squared. Because cos squared of theta plus sine squared of theta is equal to 1, and your equation becomes much simpler. But keep in mind that cos squared theta plus sine squared phi is not equal to 1. Those are two different angles. Phi and theta are two different angles. Okay? So whenever you're doing something like this and you're substituting these values in, look for cos squared phi plus sine squared phi, because that is 1. Okay? So rearrange things like that. And when you do that, again, the details are in the lecture notes. You end up with rho is equal to 2 cos phi. Right? If that sphere was centered at the origin, the equation would be rho is equal to 1. Okay, obviously, if this sphere is no longer centered at the origin, right? It's up here somewhere, right? That's rho, that's rho, that's rho. These are all the rhos to different points on the surface of that sphere. Obviously, rho is no longer constant for the sphere, right? It's a function of phi. Okay, what about another one? Let's take a look at this example. Spherical equation for z equal to the square root of x squared plus y squared. What is that? We looked at that last day. What does this thing look like? Can z be negative? Nope. So this thing lives above the xy plane. When x and y are 0, what's z? Right. When z is 1, what do you get? If I put a 1 in there for z, what does that equation look like? Square both sides, and you got x squared plus y squared is equal to 1. What's that? Circle with radius 1, right? If I make z equal to 2, what do I get? X squared plus y squared equal to 4. That's a circle with radius 2. Right? So as z gets bigger, I get circles of increasing radius. What is that? It's a cone. Exactly. I'm trying to get you to use your imagination. Got to use your imagination a little bit. Okay? That's a cone. Okay, so what are the spherical equations for this? Well, before we figure it out, let's see if we can, before we figure it out mathematically, and by mathematically I mean take these expressions up here for x, y, and z and substitute them into here. Right? That's the brute force mathematical way of doing it. Even if you didn't know this was a cone, you could just put those expressions in here for x, y, and z. You got a bunch of phi's and thetas and rhos. You try to simplify it. Voila, you got your answer. But maybe we could figure out what it is without doing that work, just by knowing that this thing is a cone. So again, look at the surface of this cone, and I mean the wall of it, not the top here. This top here is not part of the cone, right? The wall here is the cone. What's constant? If I'm thinking spherical coordinates, rho, phi, theta, what's constant on that cone? Pick a point on that cone, and then pick a different point on that cone. What's the same? Phi, exactly. Is rho the same? Nope, rho's different. Is theta the same? Nope, theta's different. But phi is the same for every point on this cone, because phi is the angle from the positive z-axis down. And that angle is the same no matter where I am on that cone. So it stands to reason that the equation here is going to be phi equal to something, some number. Okay? What do you think that angle is? What is that angle phi? Well, look back here at this equation again. I drew it at a particular angle. It's not quite accurate, so don't go by my drawing. $45 degrees, yep, which is pi by 4, right? Pi by 2 is 90. If I had this cone instead, it would still be phi is equal to something, but would phi be a bigger value or a smaller value than pi by 4? Well, think about what this cone is going to look like. Now z is 1/3 of this combination of x squared and y squared, which is going to be a smaller z value than the z value here for the same x and y, right? Which means the second cone is going to look like what? It's going to look like this. Which means phi would be what? Bigger than pi by 4 or smaller than pi by 4? bigger than pi by 4, because phi is measured from the positive z-axis down, right? And so that's going to be what? It's going to be pi by 3 in this case. Okay, so and if you don't trust yourself, go back up here, take these expressions, take this, substitute this for x, substitute this for y, this for z. In this expression here, look for all the cosquares and sine squares, right? Wherever you have cos squared phi plus sine squared phi, replace that with 1. Where you have cos squared theta plus sine squared theta, replace that with 1. And you'll get this. This will pop out at the end. Okay? Okay, so even though this cone is not spherical, its spherical equation is very simple. Okay. Any questions about that one? Okay, and I prefer to do this rather, I mean, I could show you the steps, the algebraic steps of substituting these expressions in for x, y, and z, but that's monkey work, right? We can all do that, no problem. You don't even have to know this is a cone. You don't have to understand what phi and theta and rho are to do that, okay? Anybody who knows basic algebra and trig can do that. What I'm hoping is that by explaining this, you get a much better understanding of what the spherical coordinates is and what these shapes, what these equations look like, okay? Any questions about that one? Okay, well, let's keep going because Dr. Chow is going fast in the other lecture section, so we got to keep up. Okay, and then there's some really funky shapes in the lecture notes, wrinkled pumpkins, and you can look at what the spherical equations for those are. They're a lot more complicated. Okay, so if we're going to do triple integrals, so that's spherical coordinates. If we're going to do a triple integral in spherical coordinates, we've got some function of x, y, z, and we want to do this triple integral, but we want to use spherical coordinates instead. Well, what do we got to do? Well, we've got to redefine our function so that it's in terms of rho, phi, and theta. Okay, the only way to really do that is to substitute the expressions for x, y, and z, those rho, phi's, and sine, thetas, and all that stuff, in for x, y, z in your original function, and out will come your function. It's basically going from here to here, okay, by replacing x, y, and z with their expressions of rho, phi, and theta. So that's how we go from here to here. Now we need to figure out what is this dv. Okay, we can't just assume that it's d rho, d phi, d theta. None of us are that lucky, okay? It's not that simple. There's going to be something in front of this. What is it? Well, we can use our determinant of the Jacobian to figure that out. Right, the determinant of the Jacobian, which is equal to a matrix, a 3 by 3 matrix, corresponding of the partial derivatives of x, y, and z with respect to, that's a partial derivative, sorry, with respect to rho, phi, and theta. Okay, and again, those are those expressions. We're taking partial derivatives of these expressions here. Partial derivative of x with respect to rho, with respect to phi, with respect to theta. That gives us our first row. Partial derivative, or does that give us our first column? I'd have to go back and double check. But you're taking the partial derivatives of each of these expressions with respect to rho, phi, and theta. To get your 3 by 3 Jacobian matrix, you take the determinant of that. If you don't trust yourself, you can try this on your own. We're basically going to give you this. We do give you this on the formula sheet, so you're not going to have to do this on the final exam, but okay, so if you do that and you find the determinant, you find that that gives you rho squared sine phi. Okay, so it's this here then that goes in front of d rho, d phi, d theta when we take a triple integral in spherical coordinate systems. Rho squared sine phi. In cylindrical, it was r dr d theta dz. In spherical, it's rho squared sine phi d phi d rho d phi d theta. Okay. So let's do an example. we've got this ice cream cone here. Okay, so we've got a three-dimensional volume which is enclosed by a cone, and the top is enclosed by part of a sphere. If the top was just flat, you'd probably want to use cylindrical coordinates. Because when you integrate in the z direction, it doesn't matter where you draw the line going through, it's z max is always the same if this is flat. So then it makes sense to use cylindrical. But in this case, the top is spherical. So if you would use cylindrical coordinates and integrate in the z direction, your z max is going to be a function of your r and theta, where you start, where you draw this line, right? And so you're going to have a little, z max is now a function, it's not a number. But if we use spherical coordinates, maybe it'll be easier. And it will. Because when we do spherical coordinates and we integrate, if we integrate in the rho direction, rho is the distance from the origin to some point. Okay? So if we draw an arrow through the region of integration in the rho direction, it would look something like this. Or something like this. Or something like this. What would rho min be for any of those? What would rho max be for any of those? Would it be a function of something? Or would it always be the same? It'd all be the same, right? It would be equal to the radius of this sphere, rho max. So that's why we would want to use spherical here. Okay? And then phi is going to be, you take this thing and you sweep it down in increasing direction of phi. Phi is the angle from the positive z-axis. So you take this arrow and you sweep it down like that. What would phi min be? 0. What would phi max be? It would be when you draw the line like this. That would be phi max, that angle there, which is going to be a number, right? So your limits for phi are going to be easy too. And theta, you're going to take this thing and you're going to sweep it around in the theta direction. If you're looking from the z-axis down, it's going to be 0 to 2 pi again. Okay, but we're getting ahead of ourselves. So let's bring up another picture. Okay, so there's our there's our same ice cream cone. Okay, in the xy plane here, we're going to have a circle, obviously, right? The shadow of this thing, if I put a light up here and shine it down, it's going to cast this shadow. This is going to be a circle with the same radius as the top of my cone here. Okay, so when I integrate in the rho direction, I'm going to draw a radiant arrow like this through my region of integration, starting at minim rho to max rho. Yes, sir. I'm sorry? Your microphone died. Did it? That could very well be. It did, thank you. And there's no more batteries. Oh, here we go. Okay, there we go. Is that back? Okay, great, thank you. Okay, so we're going to integrate in the rho direction first. Okay, so we start, rho is the distance from the origin to some point on the surface of this thing, okay? So obviously, you know, if I take a point up here, it's the distance from here to here, or anywhere from here to here, okay? So I draw an arrow in increasing value of rho going through my region of integration, D. The ice cream cone is the region of integration, D. I go through there and I ask, okay, where does it enter? Well, it enters at a value of rho equal to 0, and it leaves at a value rho equal to the radius of this sphere here, right? Okay, so we're going to find the volume of this thing again. So the volume is going to be equal to the triple integral of 1 dv, where dv is equal to rho squared sine phi d rho, that's not a good rho, d rho d phi d theta. Typically we go in that order of integration. You don't have to. Again, it depends on the object. In this case, the object, yeah, it doesn't really matter in this case actually. But we're going to typically go rho phi theta. Okay, so we're going to integrate, and again, this whole thing here is dv. So we're going to integrate in the rho direction first. So rho min we said is 0, and rho max is what? Well, it's the top of this cone, and we are told that this is part of the sphere rho equal to 1, and this cone here is phi equal to pi by 3. Yes, sir. Sorry. Yes, ma'am.
You said up above that the beginning of the part, like the dv is
Sine phi?
yeah, exactly.
Thank you. Yeah, I screwed up. I think I said phi and I wrote theta. Or maybe not. Thank you. Rho squared sine phi. Okay, so rho min is 0 and rho max is obviously equal to 1, right? Because this line leaves the region of integration along the spherical surface, which is defined by rho equal to 1. We were told that. Okay, so limits of integration are simple for rho. Now, rho could be a function of the other two variables, but it isn't. And one reason we use spherical is for a shape like this, we get nice simple limits. Because whether you're using Cartesian coordinates or cylindrical coordinates or spherical coordinates, always remember that the limits on the last integral you do, the outer integral, are always what? They're always numbers. They're never expressions of other variables. But the limits of these two inner integrals may be functions of other variables. Okay? The limits of this inner integral could be a function of phi and theta, or they could be numbers like they are now. The limits of this integral could be a function of theta. It could never be a function of phi because, pardon me. Yeah, it couldn't be a function of phi. I'm going to start again. This integral, once we've done this integral, rho is gone. We've integrated it out. So the limits of this second integral, the middle one, could be a function of theta. And the last one has to be numbers. It can't be a function of anything. Okay? Okay, so now we're going to integrate with respect to phi. Phi is the angle from the positive z-axis downwards. That's phi. So we take the same arrow we drew here, and we draw it where phi is min. That would be right, let's use blue. Now let's use green. That would be right there. That would be phi equal to 0. That's the minimum value of phi we can have. And where would the maximum value of phi be? Well, when that arrow looks like that, right? So phi min is what? Phi max is pi by 3, that cone. Okay? Okay, so now we're left with theta. Theta is the same theta we know from polar coordinates and cylindrical coordinates. It is the angle from the positive x-axis to some point in the xy plane. Okay? Once we've gotten rid of rho and we've integrated theta, phi, they're gone. All we're left with now is theta. And theta lives in the xy plane. So now all we got to worry about is the region, the shadow of this thing in the xy plane, okay, which is this circle. So you draw a line at some theta value and you say, okay, well, for what value of theta, where if I start at theta equal to 0 and I go all the way around to go through the whole region once and only once, theta's got to go from 0 to 2 pi, right? If for some reason this region was only half, right, which would be the case if this cone was cut in half and I only had half of this cone, well, then this shadow would only be this half circle, in which case theta would only go from 0 to pi. But we've got a whole cone, so theta is going to go from 0 to 2 pi to cover the whole thing. So 0 to 2 pi. Okay, and now you can do the integral. Let's just do it quick. We're going to integrate with respect to rho first. So we've got rho squared. Sine phi would be considered a constant when we're integrating with respect to rho. So rho squared becomes rho cubed over 3, where rho goes from 0 to 1, sine phi d theta, 0 to pi by 3, 0 to 2 pi. Okay, so I did the inner integral, integrate with respect to rho. Everything else is constant, so sine phi is a constant. So now, obviously, rho cubed over 3 from 1 to 0, or from 0 to 1 is just equal to 1. So now I'm left with sine phi, the integral of sine phi, which I think is equal to what? I got 1/3. Don't forget the 1/3. 0 to 2 pi. And the integral of sine phi would be negative cos phi, where phi goes from 0 to pi by 3, d theta. So I'm going to end up with negative cos pi by 3 minus negative cos of 0. I better not use that. Cos of 0 times 1/3. And the integral of d theta is just going to be theta going from 0 to 2 pi, which just is 2 pi. Okay, cos of 0 is 1. Cos of pi by 3, I don't remember what that is. 1 over 3 root 2? Just root 2. Yes. Thank you. So that would be cos of pi by 3. That would be a positive value, right? No, negative. Like that?
It should be a half, I think. Cosine of pi over 3.
Oh, yeah, 1 over root 2 would be pi by 4, right? Yeah. Yeah, I think so. Whatever it is. 1 minus a half is a half. 1/6 times 2 pi, pi by 3. Is that their answer? That is the answer. Okay, now we got it. Okay, that unit circle gets us every time, right? Okay, again, if you choose your coordinate system correctly, your coordinates correctly, and you get the limits simple, usually the integral is pretty simple, okay? Any questions about that one? Okay, now something I haven't said way back here when we first introduced spherical coordinate systems is that there is a limit for phi. Phi has to be between 0 and pi. Theta can be 0 to 2 pi, no problem, right? Rho can be 0 to anything, but it's always positive, right? Rho is always a positive number. It's a distance from the origin to some point. Doesn't matter the direction of that point. Rho is always positive. But phi has to be between 0 and pi. Why is that? Why doesn't phi go from 0 to 2 pi? Well, because think again, let's say if we go back to a sphere. Let's take something really simple because we're talking about spherical coordinates. If I've got a sphere, okay, and the center of the sphere is in there somewhere. If I'm going to do a triple integral where I'm going to calculate the volume of this, so it's 1 rho squared sine phi d rho d phi d theta. Okay, what are my limits of integration going to be? Well, again, I'm going to go like this. And let's say the radius of my sphere is 1. This is the sphere rho equal to 1. So my limits of integration are 0 to 1. Right? We know theta is going to be what? 0 to 2 pi. What about phi? Well, phi equal to 0 is that. Okay? And if I increase phi, it goes in this direction, right? So this would be phi equal to pi by 2, and this would be phi equal to pi. Well, why don't I want to go like this? Phi equal to 3 pi by 2. Well, when we do the triple integral, we want to trace out the volume of this region, of this sphere, once, but only once. Okay? So you draw your arrow like this, and now we're going to sweep this arrow down so it ends like that. And when we do that, at some particular value of theta, let's say we're in the ZY plane only, what are you going to get? You're going to get a half circle as you sweep phi from 0 to pi, right? So you're going to get a half circle. And it's going to be really thin, so kind of like a really thin lemon slice, right? As phi goes from 0 to pi. Now you're going to finish the integration, you're going to take this thing and you're going to sweep it all the way through the sphere by changing theta, okay? So maybe this thing is at a certain value of theta, my half slice, and then I'm going to take this half slice and I'm going to sweep it all the way through as theta goes from 0 to 2 pi. Right? If I go theta 0 to 2 pi, I will have swept out the whole sphere once, correct? Which is what I want. But now think if I take phi and I start at 0 and I sweep it all the way to pi, and then I go back up to 2 pi. Phi, okay? I sweep it through like this. So now I've got not half a lemon slice, but a full round lemon slice. And now I take this lemon slice and I sweep it through theta 0 to 2 pi. How many times will I have swept through that sphere? Twice, which is not what I want to do. I want to only sweep through it once. So that's why we have to restrict phi from 0 to pi. If we let it go from 0 to 2 pi, well then we would have to change theta to only go from 0 to pi to sweep through that sphere once. So by convention, we say phi has to be between 0 and pi. Theta, on the other hand, can be between 0 and 2 pi. And rho is always greater than or equal to 0. Good, we'll see you on Wednesday. No, today's Wednesday. See you Friday.